Okay, so in this video, we're going to prove that the language L, where L is any number of A's, where the number of A's is a perfect cube, that this language is not regular. And so here, for the sake of simplicity, we're assuming that the alphabet is A, right? And so essentially, just to wrap our heads around it, this just means that L has a consecutive sequence of A's, right? But this length of A's is always going to be a perfect cube, meaning, right? So what are perfect cubes? They're numbers, right? They start from 0 cube, then it's 1 cube, then it's 2 cube, and so on, right? So you start with a 0, right? A0 is a perfect cube because 0 is equal to 0 cube. Then A1, right? 1 is a perfect cube because 1 is equal to 1 cube. Then you have 8, right? 8 is a perfect cube because it's equal to 2 cube. Okay, now we're really, okay, no, 8 to 27, I can still do that. 27 perfect cube because it's 3 cube, and so on, right? And so this language is not regular. So the intuition as to why it might not be regular is because the number of states that we need to keep track of this cubic length continues to increase, right? So as we reach the next cubic number, we need more and more strings to verify that it is indeed a perfect cube, okay? And this unbounded requirement of states is kind of the intuition that you should get to sort of notice that this is not going to be regular. And so how do we prove this? Well, one way to prove this is using the pumping lemma. So that's what we're going to do here. We're going to prove this. So the proof is going to be by the pumping lemma. Okay, so pumping lemma, what does that mean? That means that we're going to play a game against an opponent. So our opponent will pick some arbitrary m, which is an integer that is strictly positive. Okay, we have no idea what m is. Okay, now what we need to do, oops, okay, so what we need to do is we need to pick a particular string w and l. And the only really requirement for the string w is that it has to have length at least m. But for w to be a string in L, right, it has to be a sequence of A's, right? And the sequence of A's has to be a perfect cube. Well, in this case here, what we can do to create a perfect cube is we can just take m, the integer, and then cube it, right? If we cube an integer, then that clearly is a cubic number, right? And so it's a perfect cube, right? So if we take w is equal to a m cubed, well, this is clearly an L, right? Because we can satisfy this property, right? We can satisfy this predicate function, right? Because we have am cubed, and so it is indeed true that m cubed is equal to k cubed if, in particular, we set k to m, right? And so k being set to m means that we get m cubed, which is the number of A's we have here. So that's exactly a perfect cube, right? So am cubed is an L, right? Now, our opponent decomposes the string. Opponent decomposes w into xyz, where xy is at most m and y is at least 1. Okay. Well, here it's even easier. Here, there's not even like a debate as to what y could be, because w is, what does w look like, right? So w is just a sequence of A's, right? So it's a bunch of A's, And then we know that x is here, and then y is here, and then z is the rest of the string, right? But here clearly, right, clearly y is just some number of a's. And so we're just going to give that number of a's a particular variable. So here we're going to say y has, let's say, L number of a's, okay? So the only thing we know here based on the conditions, right, based on these conditions, is that L has to be greater or equal to 1, right? So our opponent decomposes the string, and so the only thing we know about the decomposition is that we get y is a sequence of a's where the number of a's is greater or equal to 1, okay? And so now what we need to do is we need to pump the string so that the pump string is no longer an L, right? So we need to pick an I such that Wi, which is x, y, I, z, is not an L. Well, so the idea here is that we're going to have the string m cubed, and we're going to add to it the length of L, right? So we're going to add to it the length of L. And see here, I'm going to introduce something that I haven't done before. It's actually a formula, a precise formula for what the string is going to look like based on I, right? So if I'm pumping by I, then the pumped string will look like am cubed plus I minus 1 times L, right? Why minus 1? Because if I is equal to 1, right, then that means that I have I minus 1 times L is equal to 1 minus 1 times L, which is 0, right? And so that makes sense because that means that I'm not adding anything extra to the string, and I just keep the same form m cubed, right? If I have I is equal to 2, then that means that I'm adding 2 minus 1 times L, 1 extra L. 1 extra L's worth of A's, okay? And then if I is equal to 0, what should happen is that we should pump down, so we should get a smaller string, and that's in fact what happens, right? Because then we get 0 minus 1 times L, so what we're doing is we're actually taking away LA's, okay? And so what we need, right, in our case, is that we need m cubed plus I minus 1 times L not to be a perfect cube. Well, how do you do that, right? To ensure that something isn't a perfect cube, what you can do essentially is you can say, well, I know that we have m cubed, that's a perfect cube, and I know that the next cubic number, right, the next consecutive cubic number after m cubed is going to be m plus 1, right? M plus 1 cube is the next consecutive cubic number after, well, saying after is redundant, but it's next consecutive cubic number, right? And then after m cubed, so I suppose it's not that redundant, but anyways. And so what you want to do is you want to guarantee, right? The idea is that you want to guarantee that Wi is in between m cubed and m plus 1 cubed. Because if an integer is in between and not equal to two consecutive cubic numbers, then it has nowhere else to go for it to be a cubic number. So it can't be a cubic number, right? And so that's the idea that we're going to use in this case, right? And so the I that we're going to pick in this case is actually going to be relatively simple. It's just going to be 2, right? So I'm going to set I is equal to 2, and that means that W2 is equal to am cubed plus L, right? But now the actual proof, or I guess this is like a subproof within a bigger proof, is that I need to show that this is not in L. And to do that, I need to show that m cubed plus L is not a perfect cube. And like I said, to do that, I'm going to use this idea, right? I'm going to say that m cubed plus L has to be in here, where it's not equal to the lower bound and it's not equal to the upper bound. Okay? Well, how do I do this? Well, I do this by using what I know about L, right? So I do this by using what I know about L. I know that L is greater or equal to 1, right? And I also know, that L is at most M, right? It's at most M because this second condition tells me that the concatenation of X and Y is at most M, right? And so if two strings together have length at most, right? So if I have two strings together and combined they have length at most M, then for sure only one of these two strings will have length at most M, right? Because if the combination of the two, if the sum is M, right? If the sum of the lengths is M, so if you have the length of X and the length of Y, and this is at most M, then for sure both of these things are going to be at most M, because otherwise then this inequality wouldn't hold, right? And so that means I also know that L is at most M. Okay, excellent. So that means, so what does that mean, right? That means that if I take M cubed, right, I know that M cubed plus L is strictly greater than M cubed, right? Why? Because L is at least 1, right? It's at least 1, so I'm adding at least one integer unit to M cubed. And so that means that M cubed plus L has to be at least 1 after M cubed. So I have a strict inequality here. Good. And then I know that M cubed plus L is at most M cubed plus M, right? Because of this second inequality that I derived. Okay. And I know that just in general, if I have an integer M, then an integer M is always less than or equal to 3 times itself, right? So I have M cubed plus M, that's less than or equal to M cubed plus 3M. And then if I add some other stuff like 3M squared, it's also, this inequality still holds, right? So this is definitely true, right? This inequality is definitely true. And really, what you should be thinking of is what I'm trying to do is I'm trying to get a strict inequality with M plus 1 cubed. That's, so like if the fact that I added 3M and 3M squared, you're like, oh, where does that come from? Well, I'm trying to get M plus 1 cubed. And so if you expand M plus 1 cubed, I'll just write it here. If you expand M plus 1 cubed, it's M cubed plus 3M squared plus 3M plus 1. Okay, so if I compare this and this, right, this is a less than or equal because it's not a strictly less than, given that M could be, well, it can't really be 0, but yeah, I would say just to be safe, this inequality is always better as a less than or equal because you haven't realized an additional integer here. But when this becomes a strict inequality is when you get a plus 1, right? So if you have M cubed plus M, and now you compare it to M cubed, an M, then you multiply that M by 3, you add some other stuff, and now you add a 1, then this is for sure strictly greater than M cubed plus 1 because you're at least going 1 above it, right? You're at least going 1 above it because of this plus 1. And so now I have a strict inequality, okay? And so now I can say that M cubed plus 3M squared plus 1, which turns out, right, and it doesn't turn out like as a coincidence, I did this on purpose. On purpose, this is equal to m plus 1 cubed, right? And so what I have, the conclusion is that I have m cubed plus m is strictly less than m plus 1 cubed, and m cubed plus m is greater or equal to m cubed plus l, which by transitivity, right, because the inequality is transitive, that means that m cubed plus l is strictly less than m plus 1 cubed. Okay, so what this implies, it implies that m cubed is strictly less than m cubed plus l, which is strictly less than m plus 1 cubed, right? And so what that means is that we have indeed proved that m cubed plus l, the string, the length of the string, the length of the pump string is in between m cubed and m plus 1 cubed, right? So these are two consecutive, right? These are two consecutive cubic numbers. And so if I'm in between two consecutive cubic numbers, I can't myself be cubic, right? And so that means that m cubed plus l, which is somewhere here, is not a cubic number, right? And so that means, right, that means that W2 is indeed not in L, therefore L is not regular by the pumping lemma. Okay, and so this proves that L, the original string we were trying to prove, is not regular, is in fact not regular. Okay, and so this might seem a little complicated. It was mostly complicated because of this additional math reasoning, but you'll notice that the first four steps before that are actually quite simple, right? So I had an integer m, I used m to create a cubic number. Then the decomposition means that because I just have a's, y is just some number of a's. In particular, say you set that to L. Then if you pump up by just one, right, then you get m cubed plus L. And through some reasoning here, you know that m cubed plus L is in between m cubed and the next consecutive cubic number, which means that the length of the pump string is not a cubic number. Okay, so that was another example of using the pumping lemma to prove that a language is not regular.